Welcome. In this video, we're going to work on the Work, Power, and Energy Study Guide. Hopefully this will help prepare you for the test that's coming up shortly. If you want to go ahead and pause the video, you can go ahead and check your answers with the key right now. This is the key to the study guide, and I'd prefer you do it this way and work out your mistakes than using the spoiler that's coming next to get answers or to find out how to do it. We should already know the steps. But in this case, just check your answers and see if they're right. Okay, now we're going to go ahead and start the study guide. On the front of your study guide, you have an answer sheet or a known sheet. And this is basically a table so that you can fill out the stuff that you know. This way that if you have any questions about what you know as far as the roller coaster goes on in later problems, you can always reference back here to see the things that you know, and you can use in those equations. So we're going to go ahead and get started. We'll go ahead and flip over. And so we're dealing with a roller coaster that's frictionless, so we don't have to include friction in this roller coaster except for at the end. And to start off with, you are riding in a 1,250 kilogram roller coaster car, and your mass is 83.5 kilograms. Okay, the first question says, with what force must a motor exert on the roller coaster car in order to move you and it at a constant velocity? Now, we are assuming that you're lifting straight up. It says straight up here. Okay, so the things that we know is we know that the weight, so F sub g, has to equal the force of the lift. Okay? Because we've already explained that in order to lift an object, you have to lift it with exactly equal to its weight, or just a little bit over, which by significant digits doesn't really matter. The equation for weight is the mass times the free fall acceleration of gravity, which is 9.81 meters per second squared. Now the mass in this case is going to be you and the roller coaster. So if I look at my mass, it's going to be 1,250 kilograms plus my mass, which is 83.5 kilograms, times the free fall acceleration of gravity, which is 9.81 meters per second squared, down. Now we're not going to really worry about the down, just as long as we know that it points down and that we have to lift it up. Once I have this, I can go ahead and plug it into my calculator. All right, and if you recognize this calculator, it's because it's the ones I have in class, and so this is exactly what you would do on my calculators. The first thing I want to do is I want to add the masses, 1,250 kilograms plus 83.5 kilograms, which gives me a total mass of 1,333 kilograms, or 0.5 kilograms. Now I multiply that by 9.81, and I find out that the force required to lift the roller coaster is 13,081.64 newtons. Now, by significant digits, I only want to keep one, so that's 13,100 newtons. Okay, and I would go ahead and fill that in on the front. Now, how much work must the motor do in order to lift the car 253 meters to the top of the track? Well, we know that work equals the force times the displacement times the cosine of the angle between the two. We just calculated the force of being 13,100 newtons. My displacement is 253 newtons, or 253 meters. And the angle between the two, because I'm lifting straight up, that means that my force goes up and my displacement is up. So the angle between the two is just 0. So let's make that a 0. Now cosine of 0 is just 1. And so now all I have to do is do the multiplication of this. So the work equals 13,100 times 253, which gives me 3,314,300 joules. 3,314,300 joules. Now, by significant digits, I can only keep 3. So it's going to be 3,310,000 joules. Okay. So now, what is the minimum power output needed to move the car at 9.52 meters per second? Now, in this case, we're going to use a power equation. And we know that power equals work divided by time, but it also equals the force times the velocity. So in this case, I know my force is 13,100 newtons, and my velocity is 9.52 meters per second. Do the math. 13,100 newtons times 9.52 meters per second, and I get 124,712. And that's in watts. Now by significant digits, I can only have 3, so that's 125,000 watts. Once the car stops at the top of the first hill, a large spring is raised behind it. When the spring is loosed, it will do 435 joules of work on the car. So that means that the work done here is 435 joules. What will be the velocity after the work is completed? So I'm looking for the velocity. And I know that by the work kinetic energy theorem that work equals delta KE, or 1/2 mv final squared minus 1/2 mv initial squared. Now v initial is 0, so that means that whole term is 0. And so I know that delta KE, or work, equals 1/2 mv final squared. Now what I'm going to do is I'm going to start rearranging. So to find velocity, I have to get it by itself, so I'm going to move the half over, and I'm going to move the mass over. So I'm going to multiply both sides by 2, and then divide both sides by m, and then take the square root. So let's multiply both sides by 2, 2 times the work, and then divide both sides by the mass, and then take the square root, and I get my final velocity. So this is the velocity after the spring has done its work. Go ahead and fill this in. Square root, 2 times the work is 435 joules, and then divided by the mass. The mass is 1,250 kilograms plus 83.5 kilograms. So when I type this in my calculator, we're going to do it in steps. Let's take 2 times 435. And then we want to divide that by both the masses combined. So I have to use the parentheses. 1,250 plus 83.5. And then I want to take the square root, which gives me 0.8077. Now 3 significant digits, 0.808 meters per second. Okay, so that is my velocity after the spring does work on my car. It's not that much, but it's enough to get me over the hill. Now, how far was the spring compressed before it was loosed? Well, I know that the potential energy elastic equals 1/2 K delta X squared. So I want to solve for delta X. So I'm going to move the half to the other side. And then, so I'm going to multiply both sides by 2. And then I'm going to divide both sides by K. And I get PE elastic times 2 divided by K. And that's going to equal delta X squared. So I need to take the square root. And so that's going to give me delta X. Now, the elastic energy at the top is exactly equal to how much work the spring will do. So I'm going to end up with the square root of 2 times 435 joules divided by K. In this case, K over here says 152 newtons per meter. So 152 newtons per meter. So once I do my math, let's do it in steps again. 2 times 435. And then let's divide that by 152. And then let's take the square root, which gives me a 2.392 meters. And then 3 significant digits, I'm going to end up with 2.39 meters. So that is the delta X. That's how far the spring is compressed. Now we can move on to the second page. Here's the second page. And so now the car proceeds to travel down the track where it encounters a 35.4 meter high ramp. If I look at my picture, here is my ramp, 35.4 meters. And the ramp's incline is 40 degrees from the horizontal. Below the ramp, there's a tank of water. Okay, it's got sharks in it. My little attempt at being humor. With what velocity do I leave the ramp? Well, this is a conservation of energy equation or problem. So I have my kinetic energy, 1/2 mv initial squared, plus my potential energy, mgh initial, plus my spring energy, 1/2 k delta x squared, equals, and these are all initials, and my final kinetic, 1/2 mv final squared, plus mgh final, plus 1/2 k delta x final squared. Okay. Now there's some things that we need to think about. I can either choose to use the velocity that I came up with at the beginning and put it in my my initial velocity, so I have initial kinetic energy, or I can choose to before the spring worked. All right, and then in that case, this whole thing would be that 435 joules. Either way, this is going to be 435 joules, or that one's going to be 435 joules, because I didn't gain any energy in the system at the beginning. So I want to know how fast I'm moving at the end. So at the beginning, let's go ahead and just keep my velocity there. Right after the spring does its work, I don't have any more springs. Now, also, because I got rid of the springs, I can get rid of my masses from a previous problem that I've shown you. And now I know that 1/2 v initial squared plus g h initial equals 1/2 v final squared, or this is my velocity right before it leaves the ramp, plus g h final. We need to go ahead and solve for this velocity. All right, so I'm going to subtract this gh final to the other side, and so I'm going to be left with 1/2 v initial squared plus gh initial minus gh final equals 1/2 v final squared. And so now I'm going to multiply both sides by 2 and take the square root. So 2, let's go ahead and do the 1/2 times 2. That's going to give me just v initial squared plus, let's go ahead and multiply that by 2, 2gh initial minus, multiply that by 2, 2gh final equals v final squared. And now it's just a matter of taking the square root. Fill it in. I know that my initial velocity came out to be 0.808 squared plus 2 times negative 9.81. I'm sorry, you have to keep it a positive. Meters per second squared times my initial height, which was 253 meters. And then I want to subtract 2, that's a subtract, times 9.81 meters per second squared, and my final height. My final height is given by this 35.4 meters. And then I take the square root of that. Now I need to do this in steps. All right. If you have a smart calculator, you can use your calculator will do order of operations. And so 0.808 squared plus 2 times 9.81 times 253 minus 2 times 9.81 times 35.4. And then I hit the equal sign, and then I have to take the square root of it. And that gives me a velocity of 65.3. So V final equals 65.3 meters per second. Okay, so that's how fast I am traveling at the bottom of the ramp. Now, I want to know what is my velocity in both the x and y directions. Well, we know that the velocity in the x direction from kinematics is the velocity times the cosine of the angle theta. We also know that the velocity in the y direction is going to be the velocity sine of the angle theta, or the angle of the ramp. So in this case, our velocity is 65.3 meters per second. And then the cosine of the angle of the ramp, which is 40 degrees. Let's do that down here. 65.3 meters per second. Sine of 40, 0 degrees. And then now it's just a matter of typing into my calculator. 65.3 times cosine of 40 degrees. And I get 50.0 meters per second. And then if I do 65.3 sine of 40 degrees, then I get 41.97, which is 3 significant digits, 42.0 meters per second. Okay, if I spend 2.63 seconds in the air, how far did I travel horizontally? Well, I know my horizontal distance, delta x, equals my velocity in the x direction times my time. Right? And because it's projectile motion, I don't have any acceleration in the horizontal direction. So in this case, all I'm going to do is I'm going to multiply it. I don't have to worry about the acceleration part of this equation. And so my initial velocity in the x direction is 50 meters per second, and the time is 2.63 seconds. So 50 times 2.63 gives me 131.5, which is roughly 131.5, which is roughly 132 meters. All right, with significant digits. Okay, the next thing that I want to look at is it says that the ride ends with a frictionless braking system. Now, if I look on my picture here, at the end, I am at my height equal to 0. So that means my final height is 0. So I need to figure out with what velocity do I enter this braking area. Now, I can either choose this location where I already know the velocity and I know the height as my initial position, or I could use the position all the way up here at the top where I know the energy is involved there also. It's completely my choice. I don't have to worry about the path that it goes through in between. So let's pick one. Let's just use the energy here at the beginning. So I know how much energy I have here at the beginning, and I want to know that if all of this potential, both spring and elastic, how does that convert to kinetic down here at the end, where I have no spring or gravitational? So, once again, my conservation of energy equation. Okay. And I notice in this time I used x instead of delta x. They mean the same thing in this instance, so don't get confused about that. They're the same quantity. Now, just so we can get rid of the masses and we don't have to worry about the masses, we're going to take the initial velocity of being that 0.808 meters per second. All right, and then we're going to get rid of the springs. So then we have to worry about the springs in this equation, and then we don't have to worry about the masses. They go away. Now I want to solve for this case. In this case, the final velocity is down at the bottom of the ramp. So my height at the bottom is going to be 0, so that goes away. That's just a big fat 0. So now let's solve for this v final. Well, let's see what I have left. 1/2 v initial squared plus g h initial equals 1/2 v final squared. To get rid of the half, I'm going to multiply both sides by 2. And then I'm going to take the square root. So if I multiply this half times 2, I get v initial squared plus 2gh initial. And then I take the square root of it, which equals v final. So my initial velocity, so let's move that up to here. My initial velocity, 0.808 meters per second. Let's square that, plus 2 times 9.81 times my final height, or my initial height, which is 253 meters. All right, let's plug this in a calculator and do it in steps. 0.808 squared plus 2 times 9.81 times 253. And then I'm going to take the square root of it. And I'm going to get my velocity at the end of being 70.45 459, and then 3 significant digits, 70.5 meters per second. So that's my velocity at the bottom of the ramp. All right. Moving on, I'm now looking at number 10. And it says if I come to complete stop in 28.4 meters, what is my acceleration? Now this is a kinematics problem. What I'm going to use is v final squared equals v initial squared plus 2a delta x. Now I know my delta x is this, 28.4 meters. I'm looking for my acceleration, and I know my initial velocity that was given to me in the previous problem, and my final velocity is going to be 0. So I'm going to have 0 equals v initial squared plus 2a delta x. And let's go ahead and solve for a. The first thing I want to do is to subtract this v initial over to the other side. So we get negative v initial squared equals 2a delta x. And then I want to divide both sides by 2 and delta x. So I get negative v initial squared divided by 2 delta x equals a. Now my initial velocity that we came up with was 70.5. I mean negative 70.5 squared. Now I want to make sure that whenever I square this, I don't square that negative because it's only that number 70.5 that is squared. Divided by 2 and my delta x, which is 28.4 meters. So here we go. 70.5 squared divided by 2, and then I also want to divide it by 28.4. And then because there's that negative sign there, I know that it's going to make this answer negative. So I get negative 87.5. And the units are meters per second squared. That is my acceleration. What frictional force is required to stop the car? Well, because friction is the only force that's acting horizontally, I know that it's whatever force is required to give me this acceleration. So I know that force by Newton's second law equals mass times acceleration. I know my mass is going to be the combined of 1,250 kilograms plus the 83.5 kilograms. And then my acceleration is negative 87.5 meters per second squared. So let's add those up. 1,250 plus 83.5. And let's multiply that by negative 87.5. And that's going to give me a force of 116 or negative 116,681 newtons. Now I need to take significant digits, and so I need 3, so that becomes negative 117,000 newtons. What is the normal force acting on the car during this time? During this time, the car is horizontally. So I know that the normal force, Fn, is going to equal the opposite of my force of gravity. Now this is a directional problem, which means that I need to include the negative sign in my 9.81. So my mass, which is 1,250 kilograms, plus 83.5 kilograms, times the free fall acceleration, which is negative 9.81 meters per second squared. And that's going to give me a negative, but remember this negative sign here. So in order to get my normal force, I'm going to have to take the positive of that. So my normal force equals a positive 13,081 newtons, which just so happens to be the force required to lift the car, which is roughly 13,100 newtons. Okay, so that's my normal force. What is the coefficient of kinetic friction? Well, we know the coefficient of kinetic friction equals the force of kinetic friction, F sub k, divided by my normal force, Fn. So we calculated this as being 117,000 newtons, and it's actually the magnitude of my kinetic friction, and then divided by the magnitude of my normal force, which in this case is 13,100 newtons. And so the magnitude, all it means is the absolute value. So I'm going to do 117,000 and divide it by 13,100, which gives me an 8.93. And there are no units associated with the coefficient of kinetic friction. Now, how much work is done by friction? Well, work equals F delta x cosine theta. If I look at my angle theta, my displacement, delta x, is in the positive direction, but my force, F, points backwards. So what does that mean? That means that my angle theta is 180 degrees. Cosine of 180 degrees equals -1. So my work done is going to be the force of kinetic friction, which is what we found up here, of negative 117,000 newtons, times my delta x, or my displacement, and we said that was 28.4 meters. And once again, these are magnitudes. All right, we haven't really specified that, but in this case, it's the magnitude. This negative sign just means that it goes to the left. And when we talk about energies, we don't care about directions. I hope that makes sense, and I hope I'm not springing on you last minute. But it just means that we don't really care about the directions when we talk about energies. And then cosine of 180 degrees. So I take 117,000, multiply it by 28.4, and then multiply that by cosine of 180, which we said was -1, and I hit enter, and I get the work done as being 3 million, or -3,322,800 joules. Now, significant digit-wise, I can only have 3, so it's going to be -3,320,000 joules. Okay, so that's how I answered all of these questions. The negative sign on my work here just means that it's taking energy out. So I'm losing energy. That's why the object is slowing down. If you have any more questions, feel free to email me. If not, hopefully this shows you how to work the study guide. And I would probably pay particular attention to the study guide. I'm sure the test will be somewhat like it.